Hi, my name is Romeo Bruni, and today I'm really excited because we're going to build all the elements from stars. Of course, in the Big Bang, only hydrogen was created. All the other heavier metals were made subsequently to that. So hydrogen in the Big Bang, in the first 3 or 4 minutes after the Big Bang, there was a period of nucleogenesis, primordial nucleogenesis, when helium was made from hydrogen. So approximately 25% of the matter in the universe is helium, and that was made from hydrogen in the first 4 minutes. So hydrogen, Big Bang, helium in primordial nucleogenesis. The next elements, lithium, beryllium, boron, you would think that they would be made in stars, but they're very fragile and therefore aren't made in stars primarily, but they're made in a process called cosmic ray spallation, where heavier elements like nitrogen and oxygen get hit by cosmic rays, which splits them into smaller compounds, literally lithium, beryllium, and boron. So lithium, beryllium, and boron are made from cosmic ray spallation. You'll see on the internet various periodic tables expressed this way, where all the elements are expressed in terms of which star made them. So we're going to go through that now. We've done hydrogen and helium. The rest of the elements, the heavier elements higher than helium, are considered metals by astronomers. So lithium, beryllium, boron, and so on are all considered metals, and they are all made in stars. If you'll remember from a previous YouTube that I presented, stars begin as protostars. They are large molecular clouds of hydrogen that start to contract. When a star starts to contract, this is a big cloud of hydrogen. When it starts to contract, you get a pressure and temperature increase. And the pressure and temperature increase slowly progress. And the stars still, in the protostar phase, are still radiating heat, but it's no nuclear fission or fusion is going on. The heat is just from release of gravitational potential energy as it gets hotter and hotter. Now, once a star gets over 10 million degrees Kelvin in the center here, at that point you have enough heat for fusion to take place. And when you have fusion, you're going to have 4 hydrogen nuclei are going to combine in various ways so as to create 1 helium. So you have 4 hydrogen going to 1 helium. Because 4 hydrogen weigh more than 1 helium by 0.3%, actually 0.7%, sorry, so you're going to get 0.7% of the mass converted into pure energy. And this pure energy is an explosion, if you will. So stars, once they enter the main phase, are in an equilibrium where you have nuclear fusion, which is hydrogen burning to helium at the core, trying to blow the star apart, and you have gravity trying to compress the star in. So stars, once they leave the protostar phase and develop nuclear fusion and go into the main sequence, they're burning hydrogen to helium at their core, and they're in hydrostatic and thermostatic equilibrium, meaning that their temperature and size vary very little over the majority of the life of the star. Approximately 90% of a star's life is in the main sequence. Once it starts to die, it falls off the main sequence, and we'll get to that soon. So all stars begin predominantly hydrogen and helium. They all go through a protostar phase, enter the main sequence. By definition, you're in the main sequence when you're burning hydrogen to helium at the core. 90% of a star's life is in the main sequence. It falls out of the main sequence when it's finally burnt all its hydrogen to helium at the core. So now we have a star where we have, at the core, we have helium. We have no more hydrogen being burned at the core, and the hydrogen gets shoved out to a shell that's burning. So we have a hydrogen burning shell around a helium core. As soon as you've stopped burning hydrogen to helium at the core, stars move off the main sequence and are beginning to go into the dying phase. This, again, is 90% of the life of the star is in the main sequence. But once you burnt all the hydrogen to helium and you have a helium ash core, then you fall off the main sequence. All stars go through the main sequence and fall off the main sequence. When they fall off the main sequence, all stars become very unpredictable. They begin to pulsate. They lose thermostatic equilibrium as temperature in the core begins to continuously increase. And because they begin to pulsate and actually get hotter at the core, they enlarge in size and become giants or supergiants. And they will start to shed a lot of material in the form of coronal mass ejection. So stars, once they leave the main sequence, begin to pulsate, become very unstable, they grow in size, and they start to shed a lot of material. But at this point, they're still just burning hydrogen to helium, and the helium core is building and building. Once the helium core gets hot enough, and it's got to go over apparently like 100 million degrees Kelvin, then you start to burn helium. And when you start to burn helium, you'll burn helium into carbon. So the helium core now becomes a carbon core with the helium at one layer outside and the hydrogen one layer further out. In other words, the dead ash always moves to the center of the star. At first there is no dead ash, and then there's a helium dead ash. Eventually you get hot enough to start burning the helium, and you start to develop carbon in the core of a star, and et cetera up the chain. So carbon and nitrogen, as you will see in the diagram here, are from dying low mass stars because they make carbon and nitrogen in the core. Now, stars continue to do this, and depending on their weight, they'll start to vary in terms of what they do now. Stars up to approximately 4 solar masses in weight will at this point start to shed off their outer layers in the form of a planetary nebula. They'll explode off their outer layers and shrink down and become just a carbon oxygen core. And they've shed off their outer layers. At this point, they become a white dwarf. So lower mass stars will die into a white dwarf. Now, interestingly, you would think that therefore you can't get more than carbon from lower mass stars. But there is a process that in the dying phase, stars will actually start to produce higher elements in a process called the S process, which refers to slow neutron capture. And stars that do this are predominantly, let's say, in the low mass weight stars. So we have stars from 0 to 4 solar masses. And they've got carbon burning at their core, hydrogen and helium further out. And then through a process called the S process, they will use elements that have been seeded from previous supernovas, iron, etc., and start to inject neutrons into that iron to create the higher metals. So this is during the asymptotic phase of giant stars is when they do this. That's a phase that, it's a later phase of lower mass stars that are nearing the end of their death before they become white dwarfs. So that's why when we look at the elements being made, we have low mass stars producing elements higher than iron. Even though there's no iron being made at the core, these elements in the middle here are being produced by a slow neutron capture in the asymptotic phase of low mass stars. Continuing with higher mass stars, you've got carbon burning at the core. At some point, it'll get hot enough so that you start to burn the carbon at the core, and will start to form the higher elements like oxygen, fluorine, sodium, magnesium, etc. And so what happens then is that the ash always goes to the center, and you get an onion type arrangement like this, where you'll see you have hydrogen on the very outside being burned, and then the next layer in is helium being burned, and then carbon being burned, and neon, oxygen, and finally iron at the very center. Now, iron is an interesting element because up to and including iron, when you fuse elements, you get energy out. It's an exothermic reaction. So stars can continue, the massive stars could continue to burn the higher elements up into including iron, at which point to get higher elements than that, you need to actually put in energy. And therefore, stars will burn, burn, burn until they get to an iron core, the massive stars. At that point, you can't get further energy out. And so when the iron core gets big enough, in fact, when it gets over the Chandrasekhar limit of 1.44, it will collapse. And this is called a core collapse supernova. It's one of the most major types of supernova. There's two types, really, only the core collapse, which are the majority of supernovas, and another type, which we will discuss, involving white dwarfs. So in this case, you've now burnt your fuels and you've got an iron core. You can't get any more energy out of iron, and the iron starts to get extremely heavy, and then it begins to implode. And when you get this implosion, you get a rebound effect, and that's a supernova. That is a type 2 supernova, either type 2 or types 1b or c. And they are core collapse supernovas. And what's essentially happening is you get a collapse and then you get a rebound out. So these types of supernovas, not only have they produced the heavy metals, but then by the ejection of these heavy metals into the environment will seed the neighboring galaxy with heavier metals, which will then be incorporated into future stars. So the higher elements then are made in part because of slow neutron capture in low mass dying stars, but the very heavier elements, higher elements still, then are also produced by supernova explosions. Of course, you have a very important type of supernova explosion, exploding white dwarfs, which creates the elements especially around iron, cobalt, and nickel in here. And what happens there is it's a very unique type of supernova where, in essence, you have a binary system. So you'll have one star, which is a dead remnant star that we call a white dwarf. And it'll be in a binary system with usually a larger star that starts to go into its dying phase and therefore will swell up. As it swells up, it'll start to feed material into the white dwarf via an accretion disk. And the material is feeding into the white dwarf, slowly, slowly feeding into the white dwarf. And of course, all white dwarfs must be under 1.44 solar masses, the Chandrasekhar limit. And if it gets an ounce over that limit, it cannot hold itself out anymore, and it will implode, and that will set off a wild thermonuclear explosion, and the complete mass and matter in that star will be converted into iron, cobalt, and nickel and blast out into space in a type of supernova called type 1a. This is very important supernova because not only does it produce these essential elements, of course, but it's also a very valuable standard candle because the explosion always occurs at the exact same weight, so the exact same amount of matter is being converted into pure energy. So it's a standard candle that we can measure in distant galaxies and compare the apparent versus the observed, the real luminosity, and be able to calculate distances. Calculating distances in astronomy is one of the most difficult things. So that's white dwarf explosions, type 1a supernova. White dwarfs can also collide with each other, and that will produce type 1a supernova with production of the elements. You'll notice that the very, very highest elements on the periodic table are down here, the very highest elements, and they're produced by neutron-star collisions. Neutron-star collisions and supernovas create elements via the R process, which is R for rapid neutron capture. So very quickly, as opposed to taking thousands of years in a slow neutron capture, and a rapid neutron capture, either via a supernova or neutron stars merging, that gives you enough energy and higher elements so that the very highest of the elements are made via neutron star collisions. And of course, there are elements even higher than this, but they're all man-made elements, and they can only be made and last for brief milliseconds of time in massive hadron colliders. When we collide heavy elements, we can actually produce even heavier elements for a brief period of time. So if we summarize then and look at this diagram, we can see that all the heavy metals higher than helium are produced in stars. Either cosmic ray fission producing lithium, beryllium, boron, but otherwise everything else is made in stars. You have exploding massive stars forming metals via supernova. You have exploding white dwarfs forming mainly the iron, nickel, cobalt metals. And of course you have merging neutron stars producing the highest of the elements. Dying low mass stars are very important in their asymptotic phase, which is one of their later phases, where they'll actually also produce higher elements through the so-called slow neutron capture. So supernovas, stars, one way or another, are vital because they produce all the elements. The Big Bang produced hydrogen, primordial nucleogenesis produced the helium. All the higher elements are made in stars. The very highest of the elements are only via supernova explosions or neutron star mergers. That's how all the elements are made. We have stars to thank. My name is Romeo Bruni. I hope you've enjoyed this. Ciao.